Today we're going to be talking about a little known area of maths with some amazing applications.
Mathematical knots are embedded in circles and impossible to undo without cutting.
The simplest knot is the trivial knot and is a ring. There are over 6 billion known knots.
Knots have also had cultural significance. The Inca people of South America used torting knots in their culture, recording tax, storing census data, keeping track of the calendar, and for military organisation.
Each one could have thousands of threads, each bearing a pattern of knots encoding the data.
In Buddhism, the endless knot is a symbol of the intertwining of wisdom and compassion.
In Italy, the Borromean rings symbolise strength in unity. The Celtic monks decorated the Book of Kells with knots.
However, knots have never played such an important role in society as they soon might.
The mathematics of DNA of the smallest scale may soon have an impact on one of the largest.
Strands of DNA are often supercoiled or tangled. In order for DNA replication to occur, this supercoiling must be relieved by enzymes called topoisomerase.
We must stop to gain an understanding of terminology used by knot theorists. In all knots but the trivial knot, the curve will pass over or under itself at a double point.
These double points are assigned a positive or negative value based on how the strands cross. The writhe of a knot is the sum of all the double points and their signs.
The only way to undo a mathematical knot, and therefore DNA, is to cut it so that a strand lying on top is now underneath. This is equivalent to the changing of the sign of a double point.
The topoisomerase acts in this way to decrease writhe.
The minimum number of double points a knot can be reduced to without cutting is the ideal crossing number, C.
U is the minimum number of times that one strand of a knot must pass through another to unknot it, and is called the unknotting number. A knot can be written in the form Cu. So this knot is described as 3-1.
In a process known as gel electrophoresis, a current is applied across fragments of DNA, causing them to move. There is a strong correlation between the distance moved and the crossing number of the fragment.
This pattern can be used when identifying unknown fragments. It also means that we know how many double points the topoisomerases must act on.
We can also measure the reaction rate of the topoisomerases to predict how long it will take for a given strand of DNA to be unknotted.
Maths has unveiled how the building blocks of life replicate. This understanding could mean we can stop the replication of DNA in fungi, bacteria and viruses.